Okay, as I said, this is the first session. It goes from 9 o'clock to 11 o'clock. We have 2 presenters. I'll be chairing these 2 presentations. I will ask Chris to come and do the first presentations. Before I do that, I'll just introduce Chris to you guys. I've actually had the pleasure of working with Chris Harrison before. Chris is a research fellow at Swinburne with a background in computer science and electrical engineering. He has helped establish and expand sensor characterization and systems at several institutions, and that includes the one that I use at RMIT University. He is responsible for the gas sensor characterization laboratory at Swinburne. His current research focuses upon the use of hydrogen gas sensors in the energy and transport sectors, as well as digital twins for production facilities. So I'll ask you to welcome Chris, and Chris, please take it away from here.
Thanks, Elias. Let's just see if I can organize this. Hopefully get some video and some slides going. Hey, there we go. Hi, so welcome everyone. Thank you, Elias, for the kind introduction. It was quite an excellent learning experience working on the system he's mentioning at RMIT there, and really sort of sets them apart as a very bespoke facility. Even if I might have some words about the setup and running of that system towards the end of this talk. So just a bit of background about me. So as Elias mentioned, so my background's in computer science and electrical engineering. As part of that, I worked on quite a lot of embedded systems, what we would now call Internet of Things type systems, which integrated various sensors into self-contained systems. So taking a sensor, taking all of the electronics that are required to make the sensor work and get useful measurements out of it, and then tying that to a microcontroller or a microprocessor in order to record those measurements and do useful work with them. That kind of led into my PhD, which I did in microacoustic gas sensors, which are a sort of very esoteric kind of gas sensor that's extremely sensitive. And again, while I was sort of there, got sidetracked a lot, worked on a lot of side projects, and helped a lot of people build a lot of interesting things. And then that sort of led into a bit of work at Monash, where I worked at the instrumentation facility, which is now defunct, unfortunately. But the idea was it was a platform that supported researchers. We mostly did work for the physical sciences, but also the sort of biomed physiology space. And in doing so, the role was people would come to us and say, we need some specialty instrument that we can't buy off the shelf to do a particular job, and we would develop it for them. And then nowadays, I'm at Swinburne, so I came in, as Elias mentioned, on an ARENA project, building the gas sensing laboratory, and these days I'm working on hydrogen production systems. So we're looking at establishing a small lab scale production setup at Swinburne in order to better understand how we can model those such systems in software in a way that's useful to the running of real world systems. So the laboratory that we want to set up at Swinburne is going to integrate quite a bit of what we're going to talk about today in terms of test and measurement and verification, with the idea that it will help us build systems that better reflect the real world. So I've separated this talk into 2 sort of parts, well, 3 if you include the last sort of endnotes. The first part is a very sort of general look at sensors from a sort of 10,000 foot view. When I was developing this talk, I sort of had in mind that it was for people who had no background in sensing. So if you're a material scientist or a chemist and you want to integrate sensing into your projects, this will hopefully be helpful to you. And then the second half is more about doing measurements accurately and reliably. And hopefully there's something in there for people who are a bit more familiar with sensing. I think I've tried to encompass a lot of very difficult or challenging measurements that you might make. So hopefully there's a bit in it for everybody. So this sort of general overview. So when you're talking about sensors, I think it's important to remember what you're ending up with at the end of the day, which is you just end up with some black box, a device, which spits out values, right? And for that to be useful, you need to know what those values might mean. And so we have this very, very narrow view of the world with often just a single measurand, something that's coming out of your sensing device. And part of developing new sensors is a calibration and characterization procedure, which gives you some idea of what those numbers might mean. And it also gives you some idea of what those numbers might not mean. So what you can kind of exclude from your possible conclusions, given this one very sort of narrow view of the world. For chemical sensors, we can usually break them up into two sort of components. The material is where probably a lot of you are working. That's where you have developed some novel or interesting material, and it interacts with an analyte that we are interested in some way. So in the case of hydrogen, the hydrogen might come along and bond to the surface and change the material's electrical properties, or it might change its optical properties, or it might do any one number of things. But the point is that this is usually your special sauce, right? This is the thing that takes the most time to develop and is the point of your research projects. What we then put that on top of is some form of transducer. And the transducer is just there to give you a way of connecting to that material and analyzing whatever characteristic you're particularly interested in. That can be quite simple. So in the case of a lot of materials that change their conductivity, that can just be some electrodes on a substrate. But it could also be a MEMS device. It could also be piezoelectric substrate. It could be any number of things that give you various advantages and disadvantages in accessing various physical or electrical properties of the material you're trying to study. And then the next sort of thing in the stage is the instrumentation. And so that connects to your little transducer and gives you some number that you can put on a plot and figure out what's going on with your device. And in the lab, this is instruments you may be familiar with: multimeters, electrometers, picoamp meters, LCR meters. All of these things give you different data, or they give you very specific data in across a specific range, put it that way. We'll get into that a bit later. And then in the real world, when you just buy, a commercial off-the-shelf sensor, sometimes these electronics are integrated. And so instead of having like a multimeter or LCR attached to your device, it might either just output directly, or it might give you some sanitized output. So as an example, a lot of industrial systems output to either a very small current signal between 4 and 20 milliamps, or to a voltage signal between 0 and 10 volts. It's just sort of a standard that everyone agrees on. And so the sensor you're buying off the shelf has the electronics to do that conversion for you and take whatever's coming out of the sensor and sanitize it for use with other systems. So in terms of basic characterization, this is what you need to do in order to make use of any sensing device you've developed, right? Until you characterize your sensor, you really can't say much that's conclusive about its use. If I take a device I haven't characterized, put it out in the field, and I observe some change in its output, without calibration, I have no way of knowing what that information is telling me. So from a very broad view, an approach to this you might do in a quite a long series of experiments, first studying what the device might do under inert conditions when there is no analyte present, just to understand how it behaves under nothing's happening, right? If it's something that moves around a lot or it never stabilizes, then don't bother, throw it in the bin, try again. Hopefully it does stabilize, and then you can start introducing analytes, and those analytes should produce some output that you can record and understand. And in that case, the two important things to note are usually the response magnitude, how much it changes, and how fast it's done it. And these will help inform your future experiments. Then you can go through and start varying things. Like all good experiments, you should probably only vary one at a time. Otherwise, you'll end up deep in the weeds. But you can vary device operating temperature, you can vary pressure, you can vary flow rate, you can do all sorts of things in order to determine where your device operates optimally. And so if, in a publication, this is data you would include to say, look, I've done the work and I've figured out that the ideal operating point is here. But then you'll usually just pick the sort of ideal operating conditions and then run with that for the rest. Though it is important to understand how those conditions do affect your sensing performance. Once you've got that out of the way, you can either start introducing other materials, so understand how selective your device is, a term we'll talk about in just a moment, in the presence of contaminants, or you can start, again, varying the environmental conditions, making things a bit more less laboratory-like, I suppose, and make things a bit more uncontrolled and see if your device would actually be suitable for use in the real world, where often a lot of these factors are not controlled. And then finally, you repeat absolutely everything you've already done multiple times over weeks and months and years in order to determine whether or not you've made something that's particularly stable or robust. And in each step of this process, you're building confidence in that characterization. You're developing a more complete picture of the device you've developed in exactly the same way that SEM and NXRD and XPS helps you understand the material that you've made. The first term we're going to talk about is sensitivity, and with sensitivity comes linearity. Sensitivity is a measure of how much your device is changing in response to exposure to a given analyte. It's something that you'll find in literature is reported in a number of different ways, and I've listed a few examples there, although it may not be a complete list. Sometimes they may give you an absolute value. We did a measurement in inert gas and we did a measurement in gas, and we got these two different resistance values as an example. It may give you a relative value where they just say, well, if we pretend we start at 0 and the resistance changed by X number of ohms. You can normalize that to say, well, it went from 100% at the beginning and it decreased to a 50% level, or it increased to, say, 150% level. And then you can also normalize that against your starting value. So you could just say, well, from the beginning of my experiment to the end of an exposure of a particular analyte, my output changed by a particular percentage. Yeah, the sort of suitability of each of those particular measures is largely determined by the space you're working in, and also by the material you happen to be working on. If you are developing samples with drop castings, say, you may find that it's very, very difficult to get a series of devices that all have exactly the same starting resistance, right? In which case it becomes very difficult to compare different devices with absolute values because you're starting from different points. And in that case, something like a normalized or a normalized relative value might help you along. And again, looking at literature in the space you're working with, looking at literature using similar techniques to what you're using will give you an idea of what you should be targeting. And the other thing to remember here is often devices are only predictable across quite a small finite range. So although it'd be very nice to have devices with an infinite dynamic range, something that could work at, say, 0% hydrogen and 100% hydrogen. But unfortunately, that's just not how the world works. And oftentimes you'll find that devices will only work over a very narrow range. And it's up to you to locate that range and understand where you are in sort of the device's possible operating conditions. So you'll find that as concentration increases, that relationship between the gas that you're exposing your sample to and the measurement that you're making stops being linear at some point. It'll round off, or it'll get stuck. You may end up damaging your device for certain analytes. But yeah, it's just something to be aware of. In working out that sensitivity, you can also work out a limit of detection. Now, a limit of detection is an interesting thing. It's not necessarily something you might ever actually study directly. So if you perform all your characterization and you determine that your device, its limit of detection is 100 parts per billion, there's almost no point in doing an experiment there, because what the limit of detection is the boundary point at which you can say with some confidence that you have received a valid measurement versus you have just received noise, right? So at the limit of detection, you're just on that cusp of being able to say, yes, a measurement has been made. And this comes, or rather is calculated as a function of statistics. You study the performance of your device in just sort of background ambient inert conditions. And that gives you some idea of what your amount of noise in the signal is, right? And so anything that's at that level, or even a few multiples of it, is indistinguishable from nothing happening. And statistics gives us these tools to calculate confidence intervals. Normally, what you would do is take that background noise signal, calculate the standard deviation, multiply that by some factor. 3.3 or 3-ish is usually used to give a sort of fairly high confidence interval. And then you can plug that number in with your sensitivity, which gives you an amount of change per analyte concentration to figure out the minimum analyte concentration that you could possibly detect. But again, it's often it's a mathematical tool almost. It's something you will report in your paper, but you won't actually run an experiment there because, like I said, it would be almost indistinguishable from nothing happening at all. So response rate, another quite important factor to be aware of during your characterization. This is something that is difficult to standardize, I suppose. So what it is just a measure of if you started at one point and you ended up somewhere else, how long did it take you to traverse that change? And usually, because signals or responses are not perfect, right? You don't start at exactly 100 ohms and end up at exactly 200 ohms. You normally have some sort of like a steady increase and then it leveling out. We pick points that are not the sort of absolute max and min. You pick something that's like a little narrower than that. And so starting at sort of 10% of the change, going to 90% of the change is standard. That said, I did a survey of commercial hydrogen sensors recently, and I found that that was absolutely not reflected in the materials that vendors will provide to you. So out of the 36, 24 reported at the 10 to 90 time. A lot of the others either went to lower levels, and quite a few of them actually only gave you how long does it take for it to reach half of the change. And if you're especially cynical and an electrical engineer by trade, you might look at that and think, they're probably trying to hide something about their product. Like if they say, oh, well, our sensor is fantastic, it responds, its T50 is only 5 seconds. You might think, yeah, but that really doesn't tell you about how long it takes to stabilize and level out, does it? And another thing is these numbers will be different for your response time. So when you introduce a gas, how long does it take for the reading to level out, and for the recovery time? And in that survey, only a handful of different vendors reported those numbers. Selectivity is kind of the opposite of sensitivity. So you're actually looking at the same characteristic, but ideally you want nothing to happen, I suppose. So if you've developed, as I'm showing here, an acetone sensor, and you introduce other gases to that device, you would ideally see no response, right? In an ideal world, if I'm developing a sensor for acetone, I want it to respond only to acetone. Unfortunately, this is not really how chemistry and physics works. There's almost always some cross-sensitivity to chemically similar species. And it's important to study those effects, because at the end of the day, right, if you've got a sensor and you see some change in its output, you need to consider all of the possible mechanisms that might have caused that change. And cross-sensitivity to other gases is one of those things that we often just have to deal with in real-world applications. Speaking of commercial sensors, actually, that's another area that I found that a lot of vendors are particularly poor in reporting. They'll either claim that they've tested only a handful of other gases, some of which may not be be particularly relevant to the application that you're looking at. So in the hydrogen energy sector, we might be thinking about sensitivity towards hydrogen is our goal, but sensitivity towards methane as something bad. Unfortunately, those two compounds are chemically similar, and you often get some crosstalk. But yeah, the vendors will not really give you that information, or if they do, they tend to paint a particularly rosy picture of it. I know of a few vendors just off the top of my head where in their data sheets they claimed to have no response towards, I think, hydrogen sulfide. And when I ran the experiment, I found that the devices were actually damaged by hydrogen sulfide. So it actually stopped giving outputs to the gas it was supposed to. And poisoning is something you need to be aware of when you're actually running these experiments. Poisoning is the sort of irreversible change in your device's chemical structure or output that's caused by exposure to something that's attacked that surface. Yeah, it's something you just kind of have to take the risk on. Sometimes you just need to try it to see what happens. So either make a bunch of devices and make a sacrificial one, or leave those experiments right to the end because there might not be any coming back from it. Okay, so that's sort of the general overview of what you might do during characterization. And now I'm just going to go into a few details of, okay, you need to make all of these measurements. How do you actually go about doing it? So measurements is its own field, to be totally honest. The field of metrology deals with the art and the science of making measurements to varying degrees of confidence using a wide range of tools. And what I've got there is actually just a photo of some physical measuring tools that I had lying around that go all the way from a fairly simple ruler, which will work in a lot of applications and give you a very broad range, but not do a particularly accurate job, through to calipers and a micrometer and gauge blocks and optical systems, which give you more and more accuracy at the cost of range, right? They can't measure across a wide of a range, but they do give you a much nicer reading. And the reason we really focus about this is because part of what I mentioned before was you're often doing these experiments over several weeks or months or years. And so if you come back to an experiment after a month or two and you load your sample up and you try and run an experiment and you get a different result, you need to be able to say fairly conclusively the cause was, say, the material changing, right? It has nothing to do with your transducer. It has nothing to do with the cabling you've used. It has nothing to do with the particular instrument it's connected to. And so setting up your measurement with some care can help you attain that confidence. It also helps you take your work with you to other places. So if you know that a particular instrument is set up well in 2 different laboratories, you should get fairly comparable results. And I mean, that's good science, right? That we want our measurements to be repeatable and verifiable by anyone should they come and ask. Just a note on resolution and accuracy, because it's something that I have discussed with people quite a number of times. It's often quite easy to look at a particular instrument and see that it's got X number of digits and assume that, oh, okay, that means that the smallest thing I can measure is whatever scope of the least significant digit on that reading is. And that's often not the case. Resolution is just a measure of exactly that. How many digits does a particular instrument give you as an output, whereas accuracy tells you whether or not you can rely on those digits. And the two become very intertwined because for a lot of instruments, multimeters and the like, these two factors are independent. To take an example of a benchtop multimeter that I use frequently, a HP 344001A, which I've put an excerpt from the manual on the screen there, you can change the resolution independent of the measurement range and the actual accuracy that you'll be able to achieve on any one of those ranges. And so you can actually see that accuracy 1 is a function of the particular range you're looking at with that multimeter, but also it varies over time. So the longer you're doing measurements over, the sort of worse performance you're going to get. Sometimes slowing things down can help get a better accuracy and actually fill out some of that resolution. So in the case of that meter, you can read out to, I think, a few microvolts on a 1 volt signal, but you can only do that if you take quite a long time between measurements, like several seconds, because what it's doing is taking multiple successive measurements, averaging them out, and then giving you the answer. That obviously hampers your ability to do things like response rate analysis, because if you're only taking one measurement every few seconds, it becomes difficult to determine a rise and a fall time particularly accurately. So a lot of these trade-offs you'll have to make as you run experiments. And just a final note, so you may find if you go looking for instruments that there's quite a wide range out there, and with extended capability comes significantly larger price tags, right? So what we might call a 6-digit multimeter, like the little bench unit that I have, might be a few $100s. To get even 2 more digits of resolution, you go from a few $100s to a few $1,000s. Now, that doesn't mean you 100% need that for every experiment, right? Because often what's being offered in those instruments is the ability to make measure very small changes on very large signals. So at 6 digits, if you've got a 1 volt signal or a 1 ohm device, you might be able to measure down to 1 microohm, right? But with the 8.5 digit, or with a more digits, a larger instrument, you can get down into the nano ohms. Whether or not you need that, it's up to debate. Sometimes you might find that there's a different setup that can give you the same data. It might just take a little more work on sort of the front end. In sort of the first class of devices, I'd just like to talk about resistive devices. These are super common, and probably because it's quite trivial to measure, and you don't need any particularly difficult instrumentation to accomplish resistance measurements. So if you have a material that changes its conductivity, this is probably the first thing you're going to try when you're characterizing that material as a sensor. Now, you're going to have to be careful here. A lot of the time when people are working with particularly semiconducting materials, they can act resistive, but we'll get into why that might not always be the case in just a few slides. Just to pin it here, when we're talking about resistance, we're talking about devices that are linearly resistive. That means they have a linear relationship between voltage and current. If I double the current going through the device, you see a doubling of the voltage that appears across that device. Now, there's no way to measure resistance directly. So you don't, when you plug a multimeter into a device, you don't just get an ohms reading out by magic. What it's doing is it's picking either supplying a current to that device and measuring the voltage across it, or it's supplying a voltage to it and measuring the current. In the case of the multimeter I mentioned earlier, what it does is it supplies a current and then measures the voltage. So what it's doing is essentially acting like a voltmeter, which it does as part of its normal function anyway, and just in series adding a little current supply and driving some power through your device. And then it's doing the math internally, just applying Ohm's law in order to figure out what that number of ohms is. Something to be careful of, particularly with semiconducting devices, is that different measurement ranges on a lot of multimeters involves different test currents. So for a normal resistive device, this doesn't matter. Like if I do a test at 1 milliamp or 1 microamp or anywhere in between, and I just multiply the voltage divide the voltage by the corresponding current, I'll end up with the same number, right? If I take a 100 ohm resistor and I measure it, as is shown there, with a 1 volt bias or a 10 volt bias, I still get the same number of ohms once I divide it out against that factor. But that's not something that's true for a lot of semiconducting devices, which we'll discuss in a few slides. Now, in terms of like resistance measurements, if you're in the sort of couple of 100 ohm to say several mega ohm range, you really don't have a lot to worry about. Your device will work quite happily with a lot of off-the-shelf instrumentation. But a lot of times you might find that your material is particularly insulating or particularly conductive. And once we exit that sort of 100 ohm to 10 mega ohm range, you need to start considering some other factors about your measurement setup and the system as a whole. And that's because as we increase impedance being the sort of all-encompassing term for resistance, including its complex component, but we'll just talk about real components for the moment. As the impedance increases, your measured current or your measured voltage becomes, your measured current becomes smaller and smaller and smaller as a function of, it becomes small compared to the voltage you've used to stimulate that current, or if you're doing a current mode measurement, vice versa. And while it might be tempting to just say, well, just keep increasing the test conditions, eventually things will break down. So especially when we're talking about devices on the nanoscale, where you might have very small spacing between fingers and things, there's a very real risk that if you increase a bias across it too much, you'll start getting arcing and things like that, which is no good for your for any material. The other thing to consider is when your material is particularly insulating, the energy being handed around by the electron is going to try and find an easier path to ground rather than going through your signal. And so that means it might find that it's a lot easier to leak across surfaces or through materials that would not normally be conducting. And these can be very difficult to diagnose and to correct, because if you're looking at your response and you just see a lot of garbage, you might be tempted to just start shielding everything, wrapping things in conductive tape, using B and C cables instead of just like loose wires, those sorts of things. They can sometimes make the situation worse before they get better. And the reason is that if your signal is trying to escape from a conductor to its reference point, so what we would call 0 volts, but you might also call ground, then adding a shield just gives it a closer path, right? So if you're looking at really high impedance measurements, what you'll often find is instruments that are capable of making those measurements can provide a guard output. And what a guard is it's basically a shield, but instead of connecting it to ground, it's driven at very close to the voltage level of the signal you're looking at. And so the idea is if you have your signal, you have a guard, and then you have a shield next to that, there's very small potential difference between the signal you want to measure and the guard. So there's going to be very little leakage there, but there will be leakage between the guard and the shield. But that doesn't really matter because the guard is being driven independently. It's not part of our measurement, and so you can kind of ignore that. Another thing to consider is that small currents will try and sneak into your signal. So ground loops and common mode voltages are very real problems. If you are looking at your results and you start to see, say, a 50 hertz component on your output signal, it's almost certainly caused by a ground loop somewhere or by a common mode voltage getting in. These are another class of problems that are difficult to correct. Usually you can correct them by making sure everything is grounded or earthed back to a single location, which removes the possibility of there being separate paths through your instruments or computers or whatever through which current can flow. But again, it can be very challenging to identify those points and implement fixes. And then the final thing to remember is when the impedance of your device is very, very high, sometimes that can exceed the input impedance of the instrument you're using to measure it. And so this means that instead of measuring your device, which might have an impedance of several mega ohms, it's several mega ohms in series or in parallel with some impedance that's internal to the instrument. Sometimes you can configure the instrument to disable or bypass that impedance. This is classically a setting you can find in a lot of precision multimeters, is the ability to switch to extremely high input impedances, usually on the range of like 10 gigaohms. But it is something you need to be aware of and make a conscious choice to do, because a lot of instruments will not do this automatically. For very low impedance measurements, so devices that are particularly conductive, a lot of metals or heavily doped materials, you're at the opposite end of the spectrum, right? So the voltage signal you may be measuring is very, very small compared to the current. At this point, everything that's in between your instrument and your sample becomes part of the electrical circuit, right? So a wire that's normally totally irrelevant when compared to a load of a few hundred ohms in your sample becomes a significant part of the circuit. You know, a length of wire, even this long, will have a resistance in the order of ohms. And so if your sample only measures a few ohms, you'll find that that becomes only a small fraction of what the instrument sees, just because it's measuring everything between its output and your sample. The solution to that is what we would call a Kelvin style measurement, or often called a 4-wire measurement. This is where instead of using 2 probes to connect to your sample, you use 4. 2 are used as a pair to provide the stimulation signal, so your stimulation voltage, and then your stimulation current, and then the other 2 are used independently to perform the measurement. And the idea here is that you're cancelling out the effects of the cables, because although there is still going to be some loss of energy across the stimulating pair of conductors, there's a very small current flow across the sensing pair. And so because that current is so small, that series resistance of a few ohms doesn't result in a very large voltage offset. So again, this is a feature you'll find on a lot of instruments and multimeters. It's actually something you can't get around when you do LCR measurements, which is what we'll talk about next. But it is, again, another tool that you can make use of, and you really should make use of if your samples are particularly conductive. Another slightly more esoteric and difficult to work around problem is that of thermoelectric noise. You may or may not know, but thermocouples, which we use to measure temperature, are formed by the fusion of 2 dissimilar metals to a single point. And what happens there is the Seebeck effect causes very small voltages to be generated at that junction in response to temperature. So just by having any 2 metal junctions, it can be copper to gold, it could be copper to tungsten or aluminium if you have a substrate that you've patterned some electrodes on. Any one of these could be a point that generates very small voltages just as a function of temperature. So it's nothing to do with the current flowing through the wire. Sometimes these effects cancel each other out. So if you take 2 dissimilar metal junctions and put them back to back, this might generate a positive voltage, but this generates a negative voltage. So they cancel each other out. But if your setup is particularly large, so if you have, say, a positive electrode on one end of a device and a negative on the other, there could be a temperature gradient across those 2, which would make those 2 effects come out of balance. And also these junctions can form anywhere. They can form at your sample, but they could also form between the cable you've used to plug into your test instrument. Again, some instruments will have capability to correct for this. It's usually not enabled by default, so read the manual. But again, something to be aware of and to be very careful of. Okay, I'm going to have to start moving quicker. I mentioned before that resistive measurements are really only good for linearly resistive devices. And this becomes a challenge when we're doing a lot of materials research, because a lot of very interesting materials for sensing are semiconductors. And semiconductors do not have a linear relationship between voltage and current, usually. This becomes a problem because if we consider like a common semiconductor device like a diode, and I change the stimulation conditions, which we saw in the slide on resistance, and then do the math, you can see that the math makes no sense, right? If I change my stimulation conditions, then I measure the current and do Ohm's law, you get wildly different numbers for different test currents or test conditions. And as we said before, oftentimes multimeters will change their test conditions kind of silently, right? Like in the background, it'll switch from, say, a kilo ohm range to a 10 kilo ohm range. All of a sudden, the current is 10 times larger, and your measurement starts to go down, which might not make any sense. This is quite unfortunate because a lot of the reason for using semiconductor materials is to actually exploit this behavior. Sometimes you'll find that increasing a bias current or a bias voltage will give you a larger response signal, a larger sensitivity. And that's really the reason that we might study such devices. And so you've just got to be careful when taking these things and putting them onto multimeters and assuming that the number it reads is in any way representative of what's going on. Again, it's probably one of these cases where it's best to consult the literature, see if anyone has looked at the electrochemical properties of a material, where they do IV plots, and see if it forms a straight line. If it doesn't, then don't use ohms mode. What you would use instead is you can still use a multimeter, but what you do is you take an external supply and you use that as a bias. And then you put your sample in series with the multimeter in current mode with this bias across the whole stack. And you can adjust the bias up and down, and you use your current measurement as your output. And at that point, there's no point doing the calculation back to Ohm's law because, again, it'll stop making sense. The thing to be aware of is if you do this, you really need to first of all consider this as a parameter that you can vary and should study. So when you're looking at your sensitivity and other factors, you should consider what happens if you increase or decrease the bias. And when you're publishing, you need to report the test conditions that you studied and what you observed. I might just power through the slide very quickly. Conductors and capacitance and inductance. So when I say impedance, impedance is really an all-encompassing term that includes resistance, but it also includes complex valued resistances, of which capacitors and inductors are sort of very simple representative elements of complex resistances because they're able to store energy. They're normally things you can't characterize at DC, so you can't just use a multimeter to measure their properties. But what you can do is apply AC waveforms, which is what an LCR meter or a vector voltmeter or any of these sort of devices will do in order to give you a measure of the capacitance of a device or the inductance. And as a byproduct, you also happen to get series resistance or parallel resistance out of that as well. One thing just to be aware of is a lot of the time these properties are frequency dependent. So you may find that changing the frequency of that AC waveform changes its behavior. Some LCR meters will let you change that infinitely within a sort of set range. So you can do 1, 2, 3, 4, 500 hertz, no problem. A lot of cheaper units will lock you into these sort of powers of 10. And the reason for that is because a lot of off-the-shelf capacitors you might buy are characterized at those frequencies, and so a lot of devices will only work at these fixed steps. Higher frequency, again, I'll probably power through this a little bit. Some devices change their behavior drastically at very high frequencies, much higher than 1 megahertz. Again, you're applying an AC waveform, but you can start to find that devices that look resistive at DC become capacitors or inductors or any sort of thing. It really becomes a lot more complex. And all of a sudden, every part of your system becomes important to consider from a noise and a measurement standpoint, because the cable connecting a network analyzer to a sample, that is itself an electrical network with properties that change as a function of frequency. And so what we would need to do is calibrate that out. And if you change even the length of the cable, if you add an adapter, you need to start all over again and calibrate all of that out again before you can start studying another device. Okay, so I just wanted to have a couple of notes on just sensing systems in general. If you are in the situation where you are establishing a sensing laboratory, there's really a lot of things to be aware of. It really is integration hell. the job is basically connecting a whole lot of disparate instruments together into a single cohesive system, and then taking different measurements from different instruments, controlling different parts of that system in a coordinated fashion. And so you run into all sorts of fascinating and terrible problems, of which I could probably talk all day. But I suppose the important thing is to, first of all, be very fault tolerant. Like if you are writing software or you are building a LabVIEW sketch or whatever, be aware that when you ask for a particular instrument to do a thing, it may not do it. You may need to retry it. You may need to disconnect from it and reconnect again. All of these things have come up in one shape or form in the various labs I've worked in. And all you can really do is just try and anticipate what might go wrong and try and handle it. And then the other thing is to try and record everything you can. Often when things do go wrong, it's a matter of going back through like log files and things to try and determine how the fault happened and how you can avoid it in the future. Every system I've ever worked on has been an evolution. It started out quite simply and complexity grew, because trying to integrate a huge number of instruments all into one package in any other way is just asking for a total nightmare. Something I would warn people against, but also wouldn't encourage you to dismiss totally out of hand, is to beware anything that's too complex and modern out of the gate. This includes things like computers that run Windows, which might sound slightly mad, but older versions of Windows don't, which you might find in a lot of setups, actually, in a lot of universities around the world, don't do automatic updates and don't reboot in the middle of the night during your experiment. So there is some advantage in using older systems. That said, during the pandemic, our lab was able to continue to operate because we were connected to a modern Windows 10 PC that was connected to the internet. So on one hand, it invited in a lot of potential problems. Some of those problems can and did bite me when things went wrong. However, we did get quite a lot of work done during a time where we were not able to be in the lab for very long at a time, where we would not have normally been able to operate the equipment. And having gone to a lot of labs at 3 or 4 in the morning in order to correct something that might be wrong, the quality of life improvement is well worth it. Something else to just keep in mind if you are ever assembling a system is to think what you might want to add down the road. Every system I've ever worked on, somebody has said, oh, it would be good if we could add X into, usually well after the thing's built and assembled. Sometimes that's not possible. Sometimes it's extremely difficult, but it is something that we've been able to integrate to some extent in the setup that we have. Yeah, it's just some final notes. So, you know, if in doubt, try and shield everything, except, as I mentioned, things that shouldn't be shielded and should be guarded. Remember that your measurements are only really as good as the references internal to the instruments. So if you have an instrument that's particularly temperature sensitive in its reference, it will change its reading, even if the input's not moving. The references are only good when they're calibrated. So if you move from one lab to another and suddenly your readings look weird, it might be because something is out of calibration. And calibration in instruments and in your sensors is only good when it's verified. So if you do a series of experiments at the beginning of the day and you say, look, I've produced my calibration curve, let me go take this device out in the field and do some actual measurements, and then you come back and do nothing, you don't really have any confidence in those measurements because you don't know what might have happened between it leaving the lab and doing the measurements. It's only once you calibrate a second time that you actually have total concrete confidence in what you've done. And the thing to remember is ultimately physics does win. There are certain types of noise that you just can't fix. There are materials that are just too insulating. There are transducers that are just not suitable for particular materials. So sometimes you end up at a dead end and there's just nothing you can do about it, but to go back to the drawing board and start again. Just some useful resources. The Keithley low level measurement handbook is actually a really good resource for anyone trying to understand the best way to do particular like electrical measurements. There's a lot of application notes from various vendors. I've listed a few there that are some are particularly old, but they're all still totally relevant. It's also very worth reading the manuals that come with a lot of instruments. Our Pico amp meter, half of the manual is detailing just how to perform measurements accurately. We have a GitHub repository for the software I've developed for our laboratory. There's only a few libraries there at the moment, but when things get published, that's where they'll end up. Yeah, and that's sort of my piece. Thank you very much.
Thank you, Chris. That was a very nice and insightful presentation. So in terms of questions, we only got a few minutes. I'll ask the questions that come in first. Chris, the first question is from Premika. I hope I've said that correctly. It states that we're looking to use a sensor setup to measure the strain from large area that involves multiple electrodes. Can you please tell how we can measure from multiple electrodes simultaneously? Please give your advice on switch meter or multiplexer or any other devices.
Okay, so there are a few approaches. One is you could just buy a bunch of multimeters and do it that way. Some can be had relatively inexpensively. Like I said, there's usually actually a lot of ex-surplus decent Hewlett-Packard, Keithley, and Keysight multimeters that go up on eBay and the likes, or secondhand vendors and things like that. So if you do have some money to spend, that will remove some of your headache, right? Because you can just connect everything independently and be done. If you're talking about an array, that's probably not going to happen because you'll just have too many connections. Multiplexers and switches are a bit of a double-edged sword. So what these are usually devices developed not for us to use in research labs, but they're designed for test setups in industry, right? So if you're a manufacturer and you're making widgets, and that widget has 7 different voltages across it, right? And you need to verify that all of those voltages are happy and stable before you can say, great, this product is ready to be shipped out. You could take one multimeter, connect a switching matrix, and then have it just alternate between devices and go, this is fine, this is fine, this is fine, this is fine, right? And then you move on. Now, that said, we have one in our lab, a multiplexer. It's integrated with one of our multimeters, actually, and you can do all sorts of interesting things like queue up measurements. So you can say, please switch to channel 1, make a measurement, then switch to channel 2, make a measurement. And it's very handy in that respect. Something we found to be maybe not challenging, but just something to be aware of is sometimes materials will take a little while to settle in after it's been connected. So the material is sitting there doing nothing. It's acting as a strain sensor in this case, right? And so it's in a relaxed state, both physically and electrically, right? You come along and you apply your multimeter to one of those elements, and all of a sudden current's flowing through it. And so that might mean that it might take a few seconds for that reading to level out to where it's eventually going to end up, even before you start manipulating the sensor itself. So that might mean that your switching matrix does give you the ability to connect a series of independent devices to a single instrument, but you might end up scanning really slowly. So it might take, like I said, a few seconds for each one of those connections to be made, to stabilize, and then for you to get a reading out. The other thing is to remember is you won't be able to do any measurements totally simultaneously. So because you're switching from element 1, 2, 3, 4, 1, 2, 3, 4, right? If something happens and it causes 1 and 3 to shoot up at the same time, you're not going to see it at the same time because you're only looking at one instrument, one element at a time. Yeah, so like I said, double-edged sword. It's a useful tool. Keithley make a bunch of switches. Again, if you don't have a lot of money, there are quite a lot of them that end up on like surplus sites and eBay and things like this. And there's like nothing wrong with them. They're just switches. There's very little that can go wrong with the things. They're designed to be able to go through millions and millions of cycles because, again, they're usually used by industry to do sort of automated testing. So it's a good option, but there's just caveats that you have to be aware of.
Thank you very much, Chris. Again, very insightful and very informative. I'd like to ask you a question as well, just quickly before we go to the next speaker. Just for students over there when they're setting up their systems for chemical sensing. You talked about thermocouples and sometimes unreliability. In terms of making sure that our thermocouple is giving us the right accuracy, if you like, how can we test that?
So in terms of that, so there's two things going on, I suppose. So one, your system probably will have a bunch of thermocouples in it, which are acting as thermocouples, right? You have deliberately selected them to measure the temperature in some point of your system. When I was measuring the thermoelectric effect, it's usually what I'm talking about is the introduction of unintentional thermocouples, right? So if you have a signal that's very, very, very small, and along the cabling that's carrying that signal, you have a junction between dissimilar metals, it can inject a very small voltage into that signal. And so that can cause all sorts of confusion and chaos. In terms of your like thermocouples that you're putting into your system to actually use as thermocouples, usually a few things to be sort of careful of. First of all is isolation. Some thermocouples are not isolated from the electrically isolated, I mean, from the point that they're measuring. So if you put several different thermocouples all connected to the same metal thing, it can sometimes mess with the measurement. The other thing is thermocouples, because they rely on this junction of dissimilar metals to generate a small voltage, they're actually subject to that in the instruments that make measurements from them as well. So if we sort of imagine a system, right? So we have a black box that's measuring our thermocouple. Our thermocouple exists somewhere in our setup, and there's these two wires that are different metals that are bonded together at the very end of that thermocouple, right? And what we want to measure the very small voltage generated by that junction. Those wires come back into your magic black box that does your thermocouple measurement. And what exists at that boundary? Probably a connector, right? And that connector probably has dissimilar metals in it. So the metals that they use to make thermocouples are usually kind of esoteric alloys, alumil and weird things. But they're probably going to go onto a circuit board, right? And circuit boards have copper traces. So something that a lot of good thermocouple like interfaces will do is what's called cold junction compensation. And so because they know that the material coming into the box is going to be different from the copper, they can measure the temperature using another temperature sensor, usually not another thermocouple, but something just like a PT100 or a resistive device, and then do the math to figure out what voltage offset to subtract away to get rid of the effect of that connector. In terms of like, how do you know whether or not the thermocouple's working? You go back to good old calibration, right? Yeah. I think the sort of standard way of calibrating thermocouples used to be like an ice bath, right? And that sets your 0 point, and then going to some other reference, and it's usually linear across a couple of 100 degrees at least. Yeah. Great.
Thank you very much. We better move on. Thanks again, Chris, for your talk and answering.